Assalamualaikum warahmatullahi wabarakatuh, and salam sejahtera to all my students. For today's lecture, we are still in step growth polymerization, and we proceed with the synthesis of high molecular weight polymer. Okay. In order to achieve successful synthesis of high molecular weight step growth polymer, there are a few things can be considered. As we all know, in the stepwise reaction scheme, the monomers, at least two monomers, involved in step growth polymerization, right? At least two functional groups, right? So the monomers, dimers, trimers, and so on may all react together. And all that is required is that the appropriate functional groups meet in the space so that the molecular weight will slowly climbs as the small molecule water is eliminated. So in order for us to achieve high reaction rate, we must remove byproducts such as water, alcohol, HCl, and so on to drive the reaction to high conversion. And the formation of the cyclic compound can make the reaction become slow. The cyclic compound is also types of the byproduct, so we must avoid the production of byproduct. Not avoid, we must eliminate the byproduct because we want to increase the conversion. So what is the conversion actually? The conversion is the how functional group in the reaction it react, and there is interchange or the chemical reaction produced between the functional group in the monomer to produce high polymer. So basically we remove byproduct by distillation under high vacuum or by azeotropic distillation. Right, so we proceed to the next step, how to produce high molecular weight. Second step is we must use the exact stoichiometric balance. So what is the exact stoichiometric balance? Means that you have enough number of mole in a functional group. For example, if you want to produce the ethyl acetate, you will need an ethyl alcohol and acetic acid. So make sure you have a right number of mole for ethyl alcohol and acetic acid to be reacted to form an ethyl acetate. So in exact stoichiometric balance, it actually controls the monomer fit composition. If the stoichiometric balance is enough value to be reacted, enough value of the monomer to be reacted, and the equivalent of functional group will lead to favorable equilibrium. Hence, it will increase the conversion of the polymer of the reaction itself. The third one is how to increase the molecular weight by use the purity monomer. Okay, make sure the monomer you are going to use is highly purity so that there is no contamination that will affect the conversion value at the end of the reaction. And to control the monomer purity in order to get the high yield purity, we want to carry out under exclusion of oxygen, since oxidative decomposition can easily occur at the high reaction temperature. So you might want to use the oxygen. We want to control the purity or the oxidation process, right? Because when the oxidation process, it will produce byproduct which is unnecessary and will affect to the percentage of the pure yield in the last conversion in the product, last final product. And also we want to use the oxygen because we want to maintain the temperature so that the temperature won't be increased drastically, right? Okay, we have done with three methods how to increase or how to produce high molecular weight in step growth polymer. Now let's look at the next slide. Okay, if you have achieved the high molecular weight polymer and you don't want that high molecular weight produced is to be reduced, or you want to stop the production of high molecular weight, You want that level only. You want just to quench, or you want to limit the number of molecular weight. So this is the several step you might want to use by the control molecular weight in step growth polymerization methods. First is by quench the polymerization reaction. So this method, it required a rapid cooling, right? As we all know, the exothermic reaction in step growth polymerization is required heat. And then, if you want to stop the production of molecular weight, you need to use a rapid cooling when the desired molecular weight or the viscosity is attained. As we all know, as the molecular weight increase during the conversion process, the viscosity also increase because of the molecular weight increase, and routinely done in the manufacture of the unsaturated polyester. So rapid cooling means that you introduce a cold temperature suddenly to the reaction, so that the temperature will be drastically low down, because we want to control the molecular weight. The second step, use an excess of one monomer for type 2 reaction, which is non-stoichiometric quantities, which are the small excess of one monomer causes the reaction to come to a halt when only the N group of the monomer present in excess are left, because they are unable to react with each other. For example, type 2 reaction, it is a bifunctional reaction which requires two types of monomer. In a monomer, it have one type of functional group, right? For example, AA plus BB. So AA, it has a same functional group in one monomer, and BB, the second monomer, is BB, which is B, and B is the same functional group on monomer BB. So what we use only the one monomer, okay, one monomer to add it in the reaction, and routinely done in the manufacture of epoxy resin to ensure that epoxide N groups are present in the oligomer. The third one, use small amounts of monofunctional reactant. Monofunctional is the functional or the monomer that have single functional groups. And by using the small amount of monofunctional, the reaction will rendering a chain and inactive. Routinely done in the manufacture of nylon 66 for fiber manufacture by adding acetic acid as monofunctional reactant. So as we all know, the nylon 66, the 6 refers to the number of carbons in the diamine portion, and the second 6 here is the number of carbons in the diacids. So we call it as the nylon 66. Okay, now we proceed with the polyfunctional and the theory of the gelation. The tri or multifunctional monomer in step growth polymerization will result in branch or cross-link polymer. Means that if the monomer or the functional group in monomer, it contains more than 3 functional group, and it has, we call it as the multifunctional monomer. So it is the possibility for the polymer to be branch or cross-link polymer. So the molecule growth is not restricted to the directions, and the products are much more complex. Further growth can lead to gelation, which the formation of infinitely large molecule network in the reaction mixture. For example, if you have a monomer plus with A dash BB, so you will produce a polymer with cross-link structure or branch structure. The sudden onset of gelation marks the division of the mixture, into two parts with our gel and sol. And gel is defined as a molecule of essentially infinite molecular weight extending throughout the reaction mass, and the sol remains soluble and can be extracted from the gel. And the gel is actually insoluble in all non-degrading solvent. So if the monomer containing a functionality which is greater than 2 are used in the step growth polymerization, basically chain branching will result. So if the reaction is carried to a high enough conversion, so the gelation will occur. And the onset of gelation, or we call it as a gel point, is accompanied by a sudden increase in the viscosity such that the polymer undergoes an almost instantaneous change from a liquid to a gel, which is the polymer is a true network polymer, and the cross-link density will increase. For example, in the production of a polyester from a dicarboxylic acid and glycol, where the reaction mixture also contains some glycerol. So glycerol is the types of the sol, which is it is non-gel portion that remains soluble in the solvent, and the gel parts is insoluble in our solvent, and it is considered as a one molecule in the formation of an infinite network. And the sol itself, as the polymerization and gelation proceed beyond the gel point, the amount of gel increases at the expense of the sol, as more and more polymer chains in the sol are cross-linked to the gel. Okay, we proceed with the step growth polymerization mechanism. Okay, students should be able to write the repeating unit for polymer, predict the byproduct, and write the step growth polymer chemical structure. So basically, you need to know the monomer 1 and monomer B to be reacted to produce polymer. You need to know the chemical structure. For example, now we look at the production of the polyester. Look at the esterification of hydroxy acid. As we all know, to produce polyester, you need to react the diacid and diol to produce part of polyester molecule, which contains of the ester bond, and water is a byproduct produced. And in the esterification of diol and diacid, you can see that this is the formation of the OH formation here, and COOH and COOH to produce a polyester. And this one is actually hydroxy acid, so you need only one hydroxy group here to be reacted with acid. This is COO. Okay, so you will produce the polyester types which have n repeating units here. Esterification of diol and diacid chloride, we have a two functionality of the diol and one acid with the chloride functionality here. And latent polymerization actually have the ring here, ROC, which is the epoxide ring here, and CO group attached to that by using the catalyst to produce the lactone in the ring opening polymerization. This is the general mechanism in production of the polyester. So polyester is made by a reaction involving an acid with hydroxyl group